Welcome to Lecture 6 of the EETK 105 course. Today we're going to be covering Chapter 7, Part 1 in the text. But first we'd like to go over the roadmap of where we were, where we're going to, or where we are today, I should say, and where we're going. So up to now, we have been talking about DC, direct current. And we're going to be talking about AC. And we are right here today. So if we look at DC and what we've talked about so far, it's been Ohm's law, the power law, efficiency. We've talked about power flow diagrams. Where we have PN, we have P out, and power loss, P loss. We've talked about series and parallel. We've talked about just this last session, voltage and current dividers. So today we're going to talk about Kirchhoff's. That's actually double H. It's a unusual spelling. Kirchhoff, current law. Which is called the KCL. We're going to talk about Kirchhoff's voltage law. KVL. And we're going to take a little sidebar and talk about battery capacity. So all of these things we talked about applies to both AC and DC except the battery. So let's review the current and voltage divider. So we have voltage divider, current divider. So we have Vx, which is the voltage, over Rx, which is, this is the resistance of interest, over R total times the voltage source, where RT is applicable to series circuits only. Just to draw a little example of that, we would have a power supply here 20 volts. R1, I'm going to go to a finer tip here. R1, no, too fine. This 10 ohm. R2 is 5 ohm. And actually we have a resistor over here as well. This is R3. And we want to measure the voltage across R2. So we could say, back up here, our total going around the loop would be 10 ohms plus 5 ohms plus 7 ohms equal to 22 ohms. So then the voltage across R2 would be equal to 5. That's the resistance of interest, which is R2, excuse me, over 22 times 20, which equals 4.55 volts. Now let's look at the current divider. So we have the current of interest equals our total, which is the parallel piece, over Rx, and that's the resistance of interest. Okay, and we'll draw a little circuit. So we have 3 parallel resistors. R1, 2 ohms, R2, 4 ohms, and R3, 6 ohms. So we remember that a parallel combination of resistors, to solve for R total, it's 1 over RT, and that would equal, in this case, 1 over 2 plus 1 over 4 plus 1 over 6. And I could use my calculator here. So we could do 2 reciprocal plus 4 reciprocal plus 6 reciprocal, and that equals, and we take the inverse of that, and we convert it to, and that's 1.09 ohms. So this equals 1.09 ohms. So then we could solve for the current now. Sub x is equal to RT over Rx times IS. I sub s, that's our formula. And since Rx is RT1, we substitute, so the current in RT1, I'm sorry, current in R1, I'm sorry, equals 1.09 over 2 times 7, and that equals 3.82 amps. So the current in R1 is 3.82 amps. And of course that can be applied to any of those resistors. We just substitute the resistor of interest in this equation, and we'll get the current through any of those legs. So let's now talk about Kirchhoff's voltage law. Also known as KVL. And what that says is the summation drawn like that around a closed loop in that direction of all the voltages equals 0. So this is the summation. And this is the closed loop. And this is in a clockwise direction. So said another way, the summation on a closed loop of the voltage equals 0. So let's draw an example of that. We have a battery. We can put the plus sign there, but we don't have to because the long bar of the battery is always positive. And we'll put another battery, this is kind of an unusual circuit, but nonetheless, it still will work. We have a resistor, R1. We have another battery this way in the circuit. So this is 2 volts. This one is 8 volts. This is R1. And this is 6 volts. So here's how it works. We're an observer over here. And we're going to, let me get my head out of the way, and we're going to walk around the loop this way. So now we're going to add up the voltages around the loop, starting right here in a clockwise direction using the Kirchhoff's voltage law. So we'll start here, and so this battery will become a -2, and then -8, plus VR1. So we want to know the voltage across VR1 in this case. Plus 6 equals 0. Solving for VR1 equals 4 volts DC. We could have done this by inspection too, because we know we have 6 volts across here. and we know we have 10 volts across here. This is 6 volts and 10 volts. So 10 volts minus 6 gives us 4. So we solved it with an equation, and we solved it by inspection. Two ways of doing that. So one thing we want to keep in mind about when we walk around this loop and assign a plus or a minus to the battery voltages as we go through the loop. Basically, if you're an observer here and you're walking this way into a battery, that would be minus. And if you're walking this way and the battery is this way, and it's toward the positive terminal of the battery, that would be a plus. So when we go back to our equation here, that's how we determine the polarity of the battery. So now we're going to talk about Kirchhoff's current law. And it says summation of all the currents in is equal to the summation of all the currents out. So if we look at a current node, we look at all the currents in, and that equals all the currents out of a node. In other words, the gozintas must equal the gozadas. Let's look at an example of that. So if we have 2 amps going into a node, we have 12 amps going out of the node, and we have 8 amps going out of the node. We can say the summation of the currents in is equal to the summation of the currents out. So solving, we have 2 plus x, and I needed to draw this. This is our current of interest here, x. So 2 plus x equals 12 plus 8. So x equals 18 amps. So now I'd like to take a sidebar and talk about battery capacity. Capacity is current times time, expressed in ampere hours, or AH, also ampere hours. It's one and the same. The battery capacity is often stated on the battery, in the case of a lithium battery, for instance, although it may not be. But anyway, so the question is how long could you power a 30 milliamp LED for? So if we say the capacity is, in this case, we're going to have a battery with a 350 milliampere hour battery, and we want to run it at 30. Well, let's do that. So we want to drain it at a rate of 30 milliamps, I should say, times time. So time equals 350, and we're solving for time over 30, and that would be 11.6 hours. So this battery at 350 milliamp hours could power a 30 milliamp LED for 11.6 hours. So now we're going to talk about trigonometry. So if I take two magnets with a north pole and a south pole, we have lines of flux going from north to south. And let's say that we're going to place a rotor in the center here, and we'll have a wire, one going into the page here and one coming out of the page here. To help you visualize this, here I'm going to draw it in 3 dimensions as I have here. And so what we're going to do is we're going to put a wire here, like so. See if I can draw this. And we'll have an axis. That wire will spin around the axis of the rotor in this direction. So basically what we've done here is we've inserted a coil of wire between the two magnets, free to pivot around the axis. So the coil rotates and a sinusoidal current is produced in the wire. So let's look at it again in 2 dimensions. Let's go back to this other slide. So basically, let's draw this. This would rotate this way. This would rotate this way. So basically this rotating coil, this wire, would generate a sinusoidal voltage that looks like this as a function of time. The amplitude is a function of where the coil is as a function of time. The minimum occurs when the coil is across the field. So we could draw that here. At this point, this would be our minimum. Also here. And then at the end of the 360-degree cycle, we're back to here again. So we'd have this configuration of our rotor within the magnetic field, which is saying that if the rotor is aligned this way, let me get another color here, this way, you're not cutting any of the magnetic lines of flux, so no voltage is created. When it's horizontal, you are cutting across a lot of lines of flux. So that's where you would have either a maximum here, actually there's 2 maximums. There's a positive maximum and a negative maximum. In trigonometry, it's related to the unit circle. In other words, as that rotor rotates, it translates to the unit circle, and this is what it looks like. So basically there's a vector and it goes around the unit circle like this, and there's an angle theta, and you have a real axis and an imaginary axis. So if we rotate the vector around the unit circle, we could talk about a real piece and an imaginary piece. We define theta as the angle between the rotating vector and the real axis. So then we could say that the real part, the real piece, equals the cosine of theta and the imaginary part equals the sine of theta. Let's look at an example. If we have a right triangle like this with a 90-degree angle, and the hypotenuse is our vector that rotates around the unit circle, and that's a length of 1 because it's a unit circle, and we have theta. We could say that the cosine of theta equals the cosine of 50 degrees. Theta equals 50 degrees equals 0.6428. Then we can say the sine of theta equals the sine of 50 degrees, and that equals 0.766. You could verify this in another way using the Pythagorean theorem, and you've all seen that before. So a squared plus b squared equals c squared. C equals square root of, we'll plug these in for the 0.6428 squared plus 0.766 squared. So we could plug that into our calculator here. So 0.6428 squared plus 0.766 squared equals, and we'll take the square root of the answer, equals 0.9999, which basically equals 1. So we have a way of determining the physical position of the coil and what our output would be. Now let's look at a concept of a vector. A vector has magnitude and direction. It has a length and an angle, and we have our real axis and our imaginary axis. So this representation is called polar notation. So we have a vector and we have an angle of the vector. The vector can also be described in rectangular notation as well, where instead of having an angle and a length, we would have an x and a y coordinate. So this would be drawn down here as well. So that would be the x coordinate, and this would be the y coordinate. And that's called rectangular notation. So let's finish today with a discussion of trigonometry. So let's draw a triangle here, a right triangle. Always has to be a right triangle. I know that's not very straight, but that's a right angle there, if you can imagine that. So we have the hypotenuse, we have the opposite side, and the adjacent side. So the sine of theta equal to the opposite, which we're calling O, over the hypotenuse. Which is the H. And the cosine of theta equal to the adjacent, which we call A, over the hypotenuse. H. And then the tangent of theta is equal to the opposite over the adjacent. So this is a way of describing a right triangle. Of course, this can be extended to the real and the imaginary axis, as we were looking at before. This is the real, this is the imaginary. So now let's look at an example. So we have a right triangle. It's 200 in length. That is the hypotenuse with an angle theta. So we can use, and the adjacent side is 140. So we can use the cosine of theta to solve for this. Equals A over H equals 140 over 200. So if we use the inverse of the cosine to solve this problem of the cosine of theta, equals cosine minus 1 of 140 over 200. So theta equals 45.6 degrees. And you could try that in your calculator. Now we'll solve for the opposite side of the of this triangle. So we can use the tangent for that. So the tangent of theta equals opposite over adjacent. So the tangent of 45.6 degrees from what we determined before equals the opposite over 140, which then the opposite equals 142. So I think we'll stop here today. Remember that the vectors can be described in polar form or rectangular form. Next time we'll show you how vectors can be used to describe the waveform of an AC generator. We talked about it today, but we'll look at it more closely the next time. So have a great rest of your day, and we'll see you next time.